All right, y'all. So I wanted to do this in class with you as yesterday, but with all the issues we had with people not printing things very fast, I pushed off till today. So you've got this video to watch tonight. What I'd like to be able to do with you is for you not just to say, oh, well, this object has some kinetic energy. I'd like to be able to say it has this much. I want to be able to actually calculate how much energy there is. We started this last time by pointing out that the other 6 kinds besides the mechanical family are just gross. We don't want to mess with those equations, but you are going to wind up using the 3 energy equations of elastic potential, gravitational potential, and kinetic. And we started down here at the bottom of this page by looking at the 3 steps to make an equation. And the step number 1, where is it? Identify the important variables. So what actually should affect it? Should it be temperature? Should it be price? Should it be, speed? Then identifying the relationships between them, whether they are direct or indirect. Step number 3 is you're just going to squish them together. Right, so here's what I mean by this. We're going to do a real quick example. Let's just say I was trying to find the equation for x, and I found out through some logic that x is directly related to a, and x is indirectly related to b. Maybe I was doing some testing and I found that out. And my third one would be that x is, let's just say, directly related to c. Well, to figure out what that equation is, I'm going to take the 3 things, 1, 2, 3, that x is related to, and I'm just going to smash them right next to each other like this. A, 1 over b, c. And I'm just going to kind of squish them together and multiply. Now, of course, the 1 just goes away, and my formula winds up being x is a times c all over b. Right? So, like if we looked at, here, let me just move this up a little bit higher, get out of the way here. If we looked at the equation for speed, we're going to see how much this makes sense. If 2 people run for the same amount of time and one goes a further distance, we'd say that they're moving faster. So we'd say that speed has a direct relationship with distance, because if you're going faster, you cover more ground. And before you say, well, but what if you don't run as long? All else being equal, the faster you go, the more distance you're going to cover. Likewise, speed is going to have an indirect relationship, that's a terrible fraction, indirect relationship with time, because the faster you go, the less time it takes you to go somewhere. Well, but what if you, just stop. The faster you go, the less time it's going to take. And so I can smash these 2 things together to get the equation for speed, and that says that it's distance times 1 over time. And of course, that 1 just goes away, and I can actually just take this whole part, boom, and do that. You just squish the 2 variables that are related next to each other, and speed winds up being distance divided by time, meters per second, miles per hour. Well, we're going to do that today with the 3 types of energy. So we're going to look at, somebody lifting an object up and giving it gravitational potential energy. We're going to look at someone taking a spring and stretching it out like this and giving it elastic potential energy, and then we'll look at somebody sliding a box across the floor and giving it some kinetic energy. And it turns out all 3 of these are directly related to just 2 things. So with potential energy, it makes sense that the heavier the object is, the more weight it has, the more energy you're going to give it by lifting it, right? If I lift a feather over your head versus if I lift a bowling ball over your head, that's going to make a bit of a difference. The second thing that's going to matter about how much energy you give this thing is how high you lift this off of the ground. Now, weight times height, right? There's no indirect. On my examples here, I had some that with an indirect relationship, and so there was something on the bottom of the fraction like so. These are both just direct relationships. The heavier something is, and the higher you lift it. That's it. And so there's no fraction involved. It's just going to be the amount of weight of the object times the height that you lifted it. Well, with the spring, it's going to be how hard you had to actually pull, the amount of force that you used to stretch it. So a really light, easy spring, or like a rubber band, you're not going to store much energy in that thing. If you have a really stout, hard, stiff spring, you can store more energy in that. So the amount of force you use to stretch it. Also, the stretch length, let's just call it let's call it the length. The length that you're actually going to do this thing. If you stretch a rubber band 1 inch versus if you stretch it 4 inches, it gives it a different amount of energy. And so the elastic potential energy is going to be force times length. Okay. Finally, kinetic energy. If you were going to start accelerating a big weight across the floor by pushing it, the 2 things that's going to matter is how hard you push. In other words, the amount of force that you apply, and how far you actually push this thing. The distance. You can do this with your little stylus or pencil or book or something. If you just push it really lightly for a short amount of distance, it doesn't gain much speed. If you push it a lot harder for a much longer distance, like you push it all the way across the table, it's going to gain more speed. And so we say there's a relationship There's a direct relationship between those two things, and it winds up being the push force that you apply times the distance that you push it. Now, believe it or not, these three, 1, 2, and let's just go red for this third one, these are all actually the exact same equation. And if you look here, maybe I shouldn't color code it that way, we have a weight, a force, and a force. Well, guys, weight is just the force of gravity. That's how hard you're actually having to push against the pole of the Earth or wherever planet you're on. The second one that shows up in this, we got height, length, and distance. All three of those are just going to be units of length, of width, of breadth, of height, whatever. And so the summary here is that no matter which type of mechanical energy, it's going to be equal to the amount of push or pull force that you're using times the distance that you are going to apply that force. It's a crummy little parenthesis. It looks like so. So the unit for force is, of course, going to be Newton, named after Sir Isaac Newton. And the unit for distance in the metric system, you know, is going to be the meter. And so the unit for energy is simply going to be a Newton times a meter. And that's terrible, and we don't like that, so we gave it a nickname. We named it after another scientist by the name of James Prescott Joule, Joule. We abbreviate this thing with the capital J, but it's pronounced like a precious gem, like a jewel, like so. So when I come back up here to my finishing the notes up on here, units of energy is going to be the joule. Acceleration due to the gravity, well, let's not worry about that right now. We're just going to take some shortcuts. So last example. This guy right here is going to lift a 100 Newton brick, that's a fairly heavy brick, up 4 meters. Well, the energy involved in doing that is going to be a force of 100, that's the F right there, force times distance, that's an N, believe it, that's an even worse N, oh my gosh. Distance, it's going to be 100 or 400, yeah, no, I said it right, 100 newtons times a distance of 4 meters. That winds up being a amount of work of 400 joules. Now, a calorie is another type of energy that you've heard of as well. They lift this in like food labels and packaging and stuff. We're going to learn how to convert between joules and calories tomorrow. Tomorrow's lab, I'm going to have you do this over and over and over again. I'm going to have you lift a bunch of weights, and I will pay you back in Starburst. So if you burn off 5 Starburst worth of energy lifting weights, then I'll pay you 5 Starburst. All right, see you tomorrow.